Hello, everybody, and welcome to our final general track talk of the day. Your host for the session is me, Matt Haberland. Madikin is preparing for the lightning talks after this. Be sure to join us for those afterwards. Reminder, if you have questions during the talk, the chat window on the right, the best place to ask a question is raise your hand. Click on that raise hands tab, and I'll call you up on the stage after the talk is done, and you can ask your questions. We'd love to see you. If you'd prefer to type out your question, you can click on the Q&A tab instead and type out your question there, and I'll bring those up on screen and read them to the speaker after he's done. Without any more, here's Zach.
Good morning, everyone. It's just after 5 o'clock in the morning in Australia, so if I seem a little slow, forgive me. The sun has not yet risen down under. I'm going to talk about why I kind of want you to stop writing tests. And the title's a little provocative, but I'm also kind of serious that I think we actually spend too much time writing our tests and doing the manual parts of so-called automated testing. And I think by taking the scientific method a little more seriously in our software, we can do much better on that front. But let's get into it. As per the Australian tradition, I want to start with an acknowledgement of country. This is Canberra, but before I lived here and my family lived here, for something like 60,000 years, it was the traditional lands of the Ngambri and the Ngunnawal peoples, who never ceded their land and just had it colonized out from under them. I hope that it can still be a place to live and learn and teach as it has been for thousands of years. But the body of my talk, I'm going to be talking about testing. And just to define testing, it's that thing where you run your code and then check whether it did the right thing, specifically with the goal of finding bugs or regressions in your code. These are slightly different tasks. Usually when we think about testing, we think about it in terms of finding bugs, that we suspect there's some kind of error and we would like to know what it is and then fix it. But on larger projects, especially if you've got a team of programmers working over a longer period of time, as many of our open source libraries do, checking for regressions in CI on a pull request is actually kind of a separate task. Often we actually don't want our test suite to find new bugs. We just want to check that no bugs were introduced in this particular change set. And so the workflow for testing typically goes choose the inputs to test against, run the thing, and then check whether it worked. I'm going to go through some examples, but with apologies to my friend David, I am not going to use reversing a list twice. Reversing a list twice is kind of a terrible example of property-based testing. So instead, let's talk about sorting a list. Totally different. We might sort a list with something like unit tests if we, for some reason, no longer trust the sorted built-in in Python. And so here are 3 pretty standard unit tests. We check that if we sort a sorted list of integers, we get the sorted list back. We check if we sort a reversed list of floating point numbers, we get the list back, but they're floating points, so we haven't changed the numeric type. And we check that we can sort unordered lists of strings as well, that this works for any type of element that we can compare. They don't have to be numeric specifically. These seem like pretty good tests to me. But if we want to add more tests, then that's going to be a lot easier if we use something like a parameterized test with PyTest. This is maybe a little more verbose when you've only got 3 examples, but it makes it much easier to add more tests or more test cases later as you discover them. So I quite like this. But it still has the problem that we have to manually come up with the output examples for each one. And for many scientific functions in particular, you can imagine it's a little harder to sit down and write out by hand the exact correct data frame or array that you expect from some complicated operation. So how do we get out of that? Is this really automated testing? It's basically manual testing that we've taught the computer how to repeat. And I like to draw the analogy here to this thing, which is the so-called mechanical Turk. It was the first ever so-called automated chess player. It turned out, of course, that the mechanical Turk worked by hiding a very small human chess player inside of it. So the purported automation was actually just a way of disguising human labor. But one of my favorite bits about this is that Pierre-Simon Laplace actually wrote this long essay explaining how chess was actually infinitely beyond the domain of machines, because you needed this capacity to have foresight, to make decisions. And of course, a few hundred years later, we do in fact have chess playing machines. It turns out that he was wrong, that computers can do this thing. and that what was missing was kind of a technique and an algorithm to do it. And of course, a lot of computing power that they didn't have in the late 1700s. So how could we write a test where we don't know the correct output in advance? Well, one way would just be to compare it to a trusted implementation. If we have a trusted sort function, then we don't need to trust our existing sort function. We can just check they do the same thing. This is actually pretty common. You might have, for example, the single-threaded version of your code, and you can compare the results to the multi-threaded version. Or you might have an optimized routine which has some really subtle logic, and you can just compare that to a brute force version to check that they always get the same results. At least on small problems, right? Your brute force version might be totally intractable on the problem size you care about, but you can still use it to confirm that your optimized routine behaves the same way on small problems. So I quite like this style of testing, but it's not always practical. One decent fallback is just to give up on the idea that you can detect all errors and start thinking, can we detect some problems? And so for this function, we can just check that, well, if we compare each pair of elements in our output list, that output list should be sorted. That is, each element should be less than or equal to the following element. That seems pretty obvious, right? Unfortunately, if the sorted implementers were having an off day and just like forgot certain elements from the list or forgot to add them to the output, this test would still pass. It checks that the output is sorted, not that the output is the sorted version of the input. So we can just add some more assertions. We can check that the output is in order and that it's the same length as the input and that it has the same set of elements as the input. What do we think about this list? Like thumbs up for good, laughing for bad? Okay, so it's not ideal. I actually kind of like this version. It doesn't catch all possible errors. In particular, like you could sort the list 1, 2, 1 into the list 1, 2, 2, and it would detect that. But at this point, we're kind of beyond the level of like plausible bugs in sorting and more like the enterprise developer from hell hates me. That said, though, if we wanted to make sure that we can detect all of those weird kind of things, we could just go back to the mathematical definition. When you sort an input, the output must be in sorted order, and it must be a permutation of the input. Any problem with this test? Well, like, it's comprehensive. It's also super slow. Checking every possible permutation and iterating through them is really not practical. On the other hand, if we know that they're hashable, we can just shove them in a counter in linear time and compare that. And so here we have a pretty comprehensive test for sorting that doesn't depend on knowing how to sort something. We can just check whether or not we sorted it correctly directly. Congratulations, we've invented property-based testing. So our sorting function is actually defined by these two properties. We've, what we said, fully specified it, that there is no possible implementation of sorting that is correct but doesn't uphold both of these properties, or that upholds both of these properties but isn't correct. That said, like, partial specifications are still great for finding bugs. Like, I would probably just write this one in most realistic circumstances because this gets a little more complicated, unless you happen to have a special case like sorting. But the problem is, no matter how rigorously you analyze it or how well you imagine, you still have this kind of fundamental problem that if you didn't think of something when you're writing the code, you're not going to think of it when you're writing the tests. And even here, we still have this thing where we have to come up with all the inputs to our test by hand and parameterize it manually. That's where HyperFuzz comes in. And HyperFuzz is the library that I've been working on for a few years and what I'm here to talk about with you. So with HyperFuzz, we can say given one of a list of some combination of integers and floats or a list of text, the same thing should pass. And then the HyperFuzz framework is responsible for coming up with those particular examples for you. And this is going to find an example that makes that test fail. Does anyone have an idea what it is? If we have not a number in the list, then of course we're going to get something wrong. We're not going to have mixed type issues because you can compare integers and floats, And the lists of strings are going to be a separate alternative. So we have either lists of mixed integers and floats or lists of strings. But if we have a nan, then of course nan compares false when it's less than or equal to literally anything else. And so a test would fail. Hypothesis makes it pretty easy just to exclude the things that you don't want to think about. If you do want to think about what should the behavior of the sorting routine be when there are some nans in the list, it gets really messy. I recommend you try it out sometime. So I want you to write property-based tests. And so the foolproof plan is that you pip install hypothesis, or if you prefer conda install hypothesis, it's in the defaults and the conda forge channel. Skim the docs, and then I have here like profit, but you actually do have to write some tests first. Kinda, because one of the things I've been working on lately is a tool that writes your tests for you. Let's have a bit of a live demo of the Ghostwriter. So if you're like me and you like being, let's call it efficient with your programming, the hypothesis write command is here to help. And hypothesis write is pretty simple. You can pass it either a module or a particular function. You can optionally tell it about an exception, which should be allowed. And then you can tell it about various styles or test design patterns that we use. Let's have a look at what that looks like for sorting. If we write a test for our sort built-in, hypothesis will tell us there's no such thing as the sort built-in. We meant sorted. And so here we go. We have a standard-looking test. We have our imports, and hypothesis is picked up on 3 arguments to sort it. We've got the iterable, either an interval of integers or of text. We've got our key function, and hypothesis isn't quite sure how it should generate the function, so it just sticks to the default value of none. And then we may or may not want to reverse that list. And hypothesis hasn't put any assertions here, right? It's just calling the function to see whether we get any internal errors, which is a kind of embarrassingly effective method of testing, at least on my code. We can also tell hypothesis that the sorted function is idempotent. That is, if we calculate our result and then we repeat that calculation on our result, it shouldn't change. And so here we get that. We have our result and our repeat, and we assert that they're equal. And this is actually true even if we've passed the reverse flag, right? If we sort in reverse mode and then we sort the output still in reversed order, it won't change. We could also check that 2 functions are equivalent. For example, the literal eval and the eval built-in. And here we'll see a similar kind of thing where we calculate the result for each and compare them. But here we run into some of the limitations of the Ghostwriter. Like, it's not actually magic, it's just a helpful way to get started. And so we can see that we've got node or string, and that's what we pass to literal eval, but also source code for the eval built-in. And that's the nothing strategy, which you're going to have to replace with something more meaningful. In this case, I'd want to edit the code so that these arguments are just collapsed into one, and instead of generating any Unicode string, we just generate valid Python source code, preferably like valid Python source code of a literal. We can also check things like binary operators for the traditional like associative and commutative and identity elements. And that looks pretty much how you'd expect. We'll substitute in maybe like integers or finite floats here, and then put in a 0 as our identity element for addition. Finally, like round trip tests. And these are, I think, the most powerful and general ones that you're likely to run into in your code base, because pretty much everyone has properties like we want to save data and then load data, and we want to have the same data back after that, or compression and decompression, or serializing and deserializing. And hypothesis is smart enough to recognize a whole bunch of patterns and function names and go like, hey, you've asked me to write a test for the compress function, and the same module contains a decompress function. Let me just check for you that that reverses the behavior of the compress function. And so here, what we need to do is just specify binary instead of nothing again. That's because the standard library mostly isn't type annotated. And then we'd have a solid test for gzip. All right, our final example is a bit of a doozy. We're going to look at JSON encoding. JSON encoding turns out to be a lot more complicated than you might have thought once you get into the optional arguments. You can check for nan, whether you have circular behavior, an encoder class, default value, ASCII output, the indentation. Okay, the object is the one we really care about, and then like a whole bunch of different parsing keys. So I just like tidied this up a bit to get rid of all the stuff we don't care so much about. So we'll have booleans for all of these. The important bit is our object. So this is the JSON blob or JSON object that we'll be serializing. Our base case, because a JSON is a recursive type, is none or true or false or a number or a string. And then like JSON can be either lists of JSON or like a dictionary of a string to a JSON value. So let's see how this works. Do we think this test is going to fail? Like fail for laugh, pass for thumbs up. It fails. And Hypothesis has actually shown us two separate failures here. The first one is that if we allow nan and our object is nan, then of course, like when we serialize, it's not equal to itself. All right. Nan comes up a lot in this kind of test. But the other one is actually more interesting. If allow nan is false and our object is infinity, then out of range float values are not JSON compliant. It turns out when you go and look up the spec, JSON, strictly speaking, is only defined over finite numbers. And so when we tell Python to be strictly standards compliant, it refuses to serialize that out. So let's look at the fixed version. I just say like always allow non-finite numbers and then assume that the object is equal to itself. Will this pass? Man, you're all getting suspicious. This one still fails. It turns out that a list containing nan compares equal to itself until you round trip it through JSON. Digging into this, when I actually wrote the test as an example for a conference, taught me about performance optimizations in Python's list equality implementation. Basically, it starts with going like, if self is other, return true. That's the case in Python's object model. It just happens that nan breaks that a little. We also do the same kind of comparison by identity for each element to start with, so we don't recurse into it. If we started going, well, yeah. So if we have like, okay, a bit of a different text, we just exclude nan again. This comes up a lot where we're like, I know nan exists, I don't care, just stop telling me. And we run this. Do we expect the test to pass now? Yeah, you're right, it does pass now. So that's the Hypothesis Ghostwriter. I think it's pretty cool, and I hope you'll find it useful when you get started as well. New tests aren't the be-all and end-all, though. The chances are, if you're here and you care about testing, that you already have some tests and you don't just want to throw them out and start over. So I'm going to walk you through how I'd migrate a test for something like a Git repo. So this test will check that checking out a new branch makes it the active branch. And here's how I'd migrate it to property-based testing. Let's start by looking at this bit. When we check out new branch and create it, then new branch is our active branch. Well, that seems straightforward enough. But we might want to say that the actual branch name doesn't matter. So this hasn't changed the behavior of the test at all, but we've semantically kind of said for any branch name, this should be true. And in fact, we could go a little further and just say, if Hypothesis generates a branch name, which, okay, at this stage happens to only be the literal string branch name, new branch, then that should pass. We still haven't actually changed the test semantically at all yet. So our next step is to maybe go, well, if we use this in multiple tests, then we can pull it out to a function. Still haven't changed the semantics of the test yet, right? Which we're about to. If we say valid branch names are any Unicode string, they're not. They're not at all. It turns out there are many more restrictions on what a valid branch name is. And so doing that kind of forced me to go read the manual for Git's branch name format. And oh boy, without going into the details of it, if we just stick to like ASCII letters of a particular length, then we should be fine. We can't even include dashes because like leading and trailing dashes have weird behavior. At this point, I've probably opened an issue to go like, we should think that through more, but more on that later. Now let's look at this body of the test. We're going, well, set up a temporary directory and then initialize a new repository in that directory and then check out the branch name to create it. And that should be our empty branch. But we probably want to make a more general claim that if the first thing you do with a new repository is to create a branch, then that's the active branch. So this is kind of what I'd be going for as my final version of the test. I'd say, like, given any valid branch name and any repository, assuming that the branch name is not already a branch and we check it out and create it, then it's the active branch. And so this is pretty much the same like natural language claim as I made before, but I think this test actually demonstrates a lot more evidence for it than this one did. Make sense? Once you've got your tests, what do you do with them? Well, the easy thing to do is you just call PyTest on it or call unit test on it, and it will be picked up as a normal test function and run. But if you want to run for longer, you can do what's called coverage-guided fuzzing, which basically adds an evolutionary feedback to try to evolve inputs that execute all the weird corner cases of your code and then find bugs. Atheros from Google is a particularly good one for that, especially if you've got something like a C extension, because it can use coverage instrumentation for the C code as well as the Python code. HyperFuzz and PyTest are designed to run the function maybe a few hundred or a few thousand times, typically for up to a couple of seconds or a few minutes. Atheros is designed to run for hours or even days. And Hypothesis has lovely integration, right? Where you define your hypothesis test. It has this attribute, hypothesis fuzz1 input. Atheros isn't a terribly pretentious name. It's a kind of viper. So just a different species of snake. And then you fuzz it. And libfuzzer on the back end will then be responsible for tracking the behavior and generating new byte strings to feed in, which cause something else. The other fuzzing engine, which I'm kind of more excited about because I built it, is HyperFuzz. HyperFuzz is pure Python. It handles a couple of extra hypothesis features like the target or the event functions, which are usable for guided feedback custom. And unlike Atheros, which runs one function at a time, HyperFuzz will run all of your functions at once. So I actually like this much more in terms of the workflow that it gives you. In CI, you run your test suite for like a fixed amount of time. And then separately to that, you just have a server or servers constantly sitting there searching for new bugs in your entire code base. It's also got great support for the hypothesis example database, which basically means that if we find a bug using this, to reproduce it, all you need to do is rerun your tests locally. That said, fuzz1 input also has great database support. But let's have a look at a HyperFuzz dashboard that I started running just at the start of this talk. So for this example, I've actually got more cores than I do test functions. Let me zoom in a little. And so you can see that some of them are just churning through, but not discovering much in the way of new coverage, right? When we go through here, okay, it is actually increasing over time, but not by a huge amount, right? That's sometimes a little clearer on a log x-axis. But if we look at these ones up here, they're really discovering new things a lot faster. And you can kind of also see here where we went through replaying things out of the database and then continuing our process of exploration. If we wanted to go look at a particular example, we can also go look at the specific pages, maybe zoom in on things, investigate like what's happening in various areas, and also see various distinct inputs. And each input here is listed because it exhibited some kind of distinct behavior from the other ones. I have accidentally found bugs in libraries that I use or libraries that I write while running demos of HyperFuzz. That, though, is coming up on 5 minutes to go and conveniently coming up on the end of my slides. So that's kind of my perspective on how testing could be more automated, and in particular, how we could get the computers to do much of our experimentation on our code for us. I hope you enjoyed the talk, and I'm here for questions. Thank you.
Awesome, thank you. All right, let's get into the questions. We've got a few minutes. I'll start with the upvoted one. Do you have a sense of how Hypothesis interacts with test-driven development? Is it well suited for that, or does it change the style of the resulting code?
I think Hypothesis is pretty well suited for test-driven development because, in a sense, it just helps you write better test functions. So one thing that's probably different is with Hypothesis, it's much easier to write a relatively general failing test very early. If you're thinking like a red-green refactor setting, then you're likely to have, depending on how you write your test, of course, but the natural iterations are maybe a little larger because your tests will tend to cover slightly more behaviors at a time. But whether you prefer to write your tests before or afterwards, however you want to run them, HyperFuzz just helps you write better tests whenever that fits into your workflow.
All right. Next one. This is actually something I was interested in, but it's been upvoted. It sounds like this sort of testing would be more comprehensive and therefore take longer. What would you recommend? Should all these tests be run on all CI platforms?
Excellent question. So I think it's probably worth distinguishing like take longer to write and take longer to execute. I tend to find that for a given level of confidence, it's faster to write. But in terms of execution, HyperFuzz adds relatively little overhead. Usually maybe 10 to 30%, depending on what you're writing. But that said, like running your test function 800 times will take roughly 800 times longer than running it once. The compensation for that is you might need fewer test functions. So I tend to find test suites which go heavily into HyperFuzz take maybe 10% longer to 3 times longer, depending on how heavily you go in. And for some projects, I've seen like literally a single test. Black uses exactly one HyperFuzz test to generate arbitrary Python source code, and it's found 6 different crash bugs. Other projects, like which I've written, are more like 90% HyperFuzz tests. I'm certainly not going to say you should use only HyperFuzz. I tend to think run them on all of your CI platforms until you actually observe a performance problem, and then decide what to do about that then. I have seen people who have like a particular job for the property-based tests, but I kind of like knowing that they pass on all the different platforms and operating systems.
Okay. There's a question, can you limit the strings that you test to strings that match your regex?
You totally can. We have the text strategy. We also have a from regex strategy, which you pass a regular expression or compiled regex object for either bytes or Unicode, and it will generate matching strings for you. That is really easy if you think about regex as expressing a deterministic finite automata, which Python regex don't because they have back references, so it's black magic, but it works.
How should libraries that already use PyTest incorporate HyperFuzz into their test suite? And are the tests deterministic?
So PyTest is a test runner, mostly. It has some utilities like PyTest mark parameterize, which help you write your test functions. Think of HyperFuzz as like a superpowered version of the parameterize decorator. So I still run my tests using PyTest. I just write them using the HyperFuzz decorators. And one of the settings that we have is like a random seed or a de-randomized flag. So if you prefer to test the same examples every time in CI, that's absolutely doable.
Gotcha. Okay. Well, that is all from the Q&A. If anybody would like to ask another question at this point, go ahead and raise your hand. Give it just a minute there. But otherwise, everyone thank me. Let's all thank the speaker. So some emojis on there. And yeah, I guess we'll go ahead and end the session now, but please join. Thanks, Zach, and join us at 3 for Central Time for lightning talks. That should be fun too.
Thanks so much, everyone, and I'll see you around.